and you can just go ahead, Chun. Yeah.
Okay, thanks for the introduction. And sorry that I'm just be back due to some power failure in my home. Okay, today it's my pleasure here to present our paper. And this is a joint work from Peking University, Chinese Academy of Sciences, the Chinese University of Hong Kong, and Microsoft Research. Okay, and in this paper, we address flow level monitoring. We consider a typical network. There are some end hosts in the network and they are connected by switches. All end hosts and switches can execute some monitoring tasks. And there is also a centralized controller in the network to manage all the end hosts and switches. For each packet in the network, we abstract it as a key value pair. The key identifies the flow this packet belongs to, and the values indicate the information carried by this packet. And the goal of the flow level monitoring is to group packets into flows based on the flow keys and compute various statistics such as packet count, byte count, and so on. Network administrators usually hope the monitoring to be highly accurate, and at the same time, they also want to keep the resource usage limited. In previous study, we often need to make a trade-off between these two objectives, but in this paper, our goal is to achieve both full accuracy and resource efficiency. For full accuracy, we expect the monitoring can cover all time intervals, all devices, and record all flows. And for each recorded flow, we also expect that its statistics are computed with zero error. Such full accuracy can benefit many network management applications because full accuracy can avoid noisy interference due to the measurement error. So eventually, the efficiency of network management will be improved. For resource efficiency, we observe that each type of entities in the network have its unique resource limitations. So we want to avoid resource overload in all of them. For end hosts, they have sufficient memory, and their CPUs provide great flexibility to realize arbitrary processing logics. However, we need to control the complexity because the CPU is a bit slow when processing the high-speed network traffic. In addition, end hosts have limited visibility. They have no information about the network internals. Switches, they can process traffic at line rate with the switch ASICs. However, the memory in switches is limited, and there are many restrictions on their programming models. And for the controller, it can integrate computational resources of multiple physical servers to form a cluster. It also has the global view of the network. However, the link capacity between the controller and each data plane device is limited. So we cannot transmit too much traffic to the controller. Given the various and tight resource restrictions, existing approaches often make a trade-off between the resource efficiency and full accuracy. One extreme is the classical SNMP techniques. They consume very few resources, but they are too cost-gram to provide accurate results. Another extreme is the hash table. Hash tables achieve full accuracy by exactly tracking each flow. However, per flow tracking exceeds the memory capacity of switches, so hash tables can only be deployed in end hosts. Between the two extremes, there are many approximate approaches that trade off accuracy to reduce resource overheads at different errors. For example, sampling, event matching, and top K counting reduce overheads by only monitoring a subset of flows. However, their results are not complete because a large number of flows may be missing. Another class is sketch. Sketch techniques allow multiple flows to share counters to reduce memory overheads in switches. However, the accuracy of sketch techniques remains approximate due to the flow conflicts. So different from these approaches, our goal is to achieve both resource efficiency and full accuracy at the same time. Before presenting our design, we first analyze the root cause of the resource and accuracy trade-offs. We find that existing solutions usually deployed operators in end hosts and switches This is a very common approach to reduce the overheads of the controller. However, the operators in each device is executed individually and lacks of collaboration. For example, an end host cannot control the processing behavior in any switches. In this case, the operator in each device has to contain complete functionalities, including flow key extraction, value checking, and resource allocation. This makes the operators very heavy, so they have to sacrifice accuracy to fit the resource limitation of the devices. So based on these two observations, we are motivated to optimize the two design choices in existing solutions, heavy individual operators and limited collaboration. So in this paper, we present Onimon an architecture to achieve our goal. Our key idea is to redesign the underlying architecture of flow level monitoring. Instead of deploying the complete functionality in each device and executing them individually, we collectively employed all entities in the network to build a distributed telemetry system. In particular, we want to answer these two questions about the architecture. These two questions are raised from the perspective of distributed systems. The first question is how to distribute network telemetry across different entities and coordinate these entities. And second, as in common distributed systems, we need to deal with some unreliable issues such as inconsistency and message loss. This is necessary to guarantee our distributed telemetry architecture works correctly. We first consider the first question. Our answer to this question is to follow the split and merge principle to propose a novel architecture for flow level monitoring. We divide the network-wide monitoring into 4 partial operations. Each partial operation is responsible for a piece of monitoring logics. This breaks the heavy individual operators in traditional solutions. Then we coordinate the resources of all network entities to realize these partial operations in a distributed manner. The coordination ensures that the 4 partial operations will eventually form zero-error results, and at the same time, the resource consumption is limited in each device. Now I will introduce how these 4 partial operations are realized one by one. For the first operation, flow key tracking, we observe that we only need to record the flow key once in each flow key once in the network. Thus, we record the key of each flow in its source and host. Then the second operation is the flow value updating. We check flow values in both end hosts and switches. In each device, we allocate some slots of counters to store flow values. There are 2 types of slots designed for egress traffic and ingress traffic, respectively. And when a packet arrives in a device, we select 1 or more slots and then update their values based on the packet. The third partial operation, flow mapping, determines how a flow associates with its slots. Since the resource constraints in end hosts and switches are different, we employ different strategies here. For end host, each flow has its dedicated slot because the memory is sufficient in end host. Since the flow keys are also checked in the source, we organize the flow keys and egress slots as a hash table. But in the destination and the host, the flow keys are not checked for ingress slots. So to solve this problem, for each flow, we embed its location in the hash table as a host index in the packet header, and the destination host can extract this index to locate its slot. In switches, since the memory is limited, we allowed multiple flows to share a same slot. This is very similar to Sketch. However, Sketch algorithms compute slots by hashing the flow key at switches. Our approach is different. We compute the switch slot by coordinating the controller and end host, but not as switches. Since the controller has the global view of the network, this can significantly reduce the conflicts at switches. And when the switch indexes are computed, they are recorded in the hash table in the source and hosts and also embedded in the packet header. Each switch extracts the index and updates the corresponding slots with the packet information. The final partial operation, collective analysis, is performed in the controller. It collects results from all end hosts and switches to form the final flow statistics. Since the slots at the switches can be shared by multiple flows, to achieve full accuracy, collective analysis also needs to restore flow values from the shared slots. Recall that in each end host, we have recorded flow keys and flow values with dedicated slots. So our basic idea is to decompose the shared slots in switches with the aid of end host information. Here we present an example. Consider a switch slot with value 24. This value must be contributed by multiple flows. Fortunately, we have recorded flow keys and flow values with 0 error at each end host. And we also record the switch index for each flow. So we can find which flows are actually mapped to these slots. In our example, there is a flow 1 with value 13 and a flow 2 with its value 11. So we can decompose the value in the switch slot into the two flows according to the source and the host information. So far, we have introduced the 4 partial operations. In summary, the resource usage is acceptable in each type of network device. In end hosts, the memory is sufficient to host per flow hash table, and the hash operation is acceptable for general CPUs. In switches, we only extract switch index and update the counter. Both operations are supported by commodity switch ASICs. And since we let flows to shared slots, the memory consumption is also limited. In the controller, we mainly leverage its global view to allocate slots and perform collective analysis, so the resource consumption is also acceptable. Now let's move on to the second question about the reliability guarantees. In this paper, our architecture faces 2 challenges from the unreliable network events. First, network monitoring is usually executed based on time intervals, but we do not have a global clock to synchronize time intervals across devices. And second, packet loss is very common. So in some devices, the flow values may not be recorded correctly. In previous studies, these 2 issues do not become a big problem because previous studies have limited network-wide collaboration. However, in ONIMO, we need to deal with them. Otherwise, the architecture may fail to work. Here we present an example to illustrate the impact of the 2 reliability issues. Here we have 2 flows with their values 13 and 11 respectively. These 2 flows shared a slot in switches. Ideally, the value in the 2 flows should be recorded in the switch. So the expected value in the switch is 24. However, if some packets exhibit long network delay, part of flow values may be included in different time intervals after the long delay. And another case is the packet loss. With packet loss, some values are even not recorded in the switch. In both cases, the value in the switch may be long. In our example, the value in the switch is now 20. Since there are multiple flows with long values, we cannot decompose the value in the switch because we do not know the actual contribution of each flow. We propose 2 mechanisms to address the 2 challenges. For the lack of global clock, we propose a hybrid consistency model to synchronize time intervals. By hybrid consistency, we mean that it's a strong consistency in most of the time, but it will be degraded to weak consistency at some times. And similar to our architecture design, the hybrid model also coordinates all entities in the network. It provides two guarantees. The first guarantee is that each packet is included in the same interval by all devices in its path. And second, it also guarantees that all entities reside in the same time interval in most of the time. And for packet loss, we propose a linear system to infer the loss. We also propose a flow mapping algorithm to make the linear system correctly works in general cases. And here I skip all the details, and you may find more results in our paper. We built a prototype of Omnimon with DPDK and before. We conduct trace-driven evaluations in both testbed and simulation environments. We first measure the host overheads. We compare Omnimon with package-gen that is also implemented by DPDK. Since package-gen has no monitoring functionality, we use it as the baseline. In the left figure, even when we add the end host monitoring functionality, the throughput drop is less than 10% compared to the original package-gen. And in the right figure, we profile the overheads. We find that the most overheads comes from hash lookups, but the overall CPU resource spent in each packet is less than 40 cycles. The next experiment is switch overheads. We deploy Omnimon and compare it with 4 recently proposed sketch techniques. Here, each sketch technique only monitors packet count, and we also have 2 versions of Omnimon. One simple version also only monitors packet count, but another full version monitors 9 types of statistics in one configuration. We observe that Omnimon consumes less resources than sketch techniques because Omnimon does not perform hash functions or record flow keys. And Omnimon can achieve full accuracy, but sketch can only provide approximate results. And we have more experiments such as the overheads in the controller, the efficiency of our reliability guarantees, and 3 use cases on anomaly detection, failure diagnosis, and load balance evaluation. And in summary, we propose the Omnimon architecture with 2 reliability guarantees. And we also build a prototype and conduct experiments to compare it with 11 state-of-the-art solutions in various aspects. And our source code is also available now. And you may download if you are interested. Okay, that's all of my talk. Thanks for your attention.
Okay, thank you for the nice presentation. Any question? So Chuan, I have a question. So, about how to make consistency between different switches. Yeah, just this slide. So, you mean that okay? The details of your solution, just we can read your paper. I just have a rough question. So you say that you just divide the into different time slots. So what's the granularity of this time slot?
Okay, that's a very good question. The key idea is that here we in our consistency model, we assign different loads to the different entities. For end hosts, they actually determine the time intervals. And because end hosts have very powerful CPU, so they can run very complicated consistency protocols. And after the time interval is determined by the end hosts, an end host embed this time interval information in each packet. So each switch in the path only extracts such time interval information from the packet and update the corresponding time slot in its memory. So the switches are just a follower in our protocol, and the end hosts are the actual proposer of the time interval. And there is we also use the controller to help the synchronization because there may be some straggler in end hosts, and the controller will identify this straggler and push the clock in the straggler to catch up with other end hosts. Oh, so this is our key idea.
Okay, thank you. Okay, Chen has a question. Yeah.
Okay. Thank you for your inspiring talk. Actually, I'm just a little curious about one thing. Are there any design behind deciding which flows should share a switch slot? Do we just do the equal split, or any considerations for that?
Sorry, I cannot hear clearly. So can you repeat your question?
Yeah, sure. In short, which flows should share a switch slot? Are there any design behind that?
Yes, we have such a design. This is determined by the controller, and since we need to decompose the slots in the switches into individual flows, so the controller can know how to make these flows. How to make these flows share the slots with the minimal flow conflicts, so that we can decompose them very efficiently. So we have such a mechanism, and it's based on it's determined by the controller. And after the controller computes the slots for each flow, and the controller sends this message to end host. So the end host can embed this information in each packet, and the switch will extract this information and update the corresponding slots.
Okay, thank you very much.
Okay, any other question? Okay, if not, let's thank Chun for the nice talk.
Okay, thank you.
Okay, the following 3 talks in our session are all from very young people. They are either undergraduate students